So just how big is the universe? Short answer, very. Generally, physicists talk about two different kinds of universes. One, the observable universe, and two, the entire universe. That is usually just called, well, the universe. The observable universe is a spherical region of the universe consisting of all matter, baryonic and non-baryonic, that can be observed from Earth at this point in time, i.e. the present. This is because light, or electromagnetic radiation from these distant celestial objects, have had time to reach Earth since the Big Bang. That is to say, anything that's too far away we simply cannot observe, as light has not had the time to travel here yet. It's simply too far. We know from the Planck satellite, launched in 2009, that the most recent measurement of the age of the universe is approximately 13.8 billion years old. If one was to assume that the universe is static and unchanging, then we could simply say that the observable universe has a radius of 13.8 billion years, as that's how much time light has had to travel. Now, the idea of a static universe is not new. This is called the steady-state model of the universe, and was widely accepted in the mid-20th century as it had a certain appeal. In this model, the universe has no beginning and thus no end. Hence, it is eternal. The idea of a static universe goes back a long time. For example, in the 13th century, where Siger of Brabant authored the thesis "The Eternity of the World," argued that there was no first man and no first specimen of any particular, that the physical universe is thus without any first beginning and therefore eternal. This was more or less what physicists believed for a long time, including the likes of Albert Einstein among others. However, Edwin Hubble discovered that the vast majority of observed galaxies are moving away from us and are not static. He did this by studying Cepheid variables. Cepheid variables are a special type of star as they pulsate over a particular time span, which made them unique, as by observing them it was possible to not only calculate how far away the Cepheid are from us, but also the recessional velocity of the galaxy that it's in. Hubble plotted this, and we have named this recessional velocity the Hubble constant, named after him. Today, we measure Hubble's constant to be around 72 kilometers per second per megaparsec. Now, Hubble's result was actually very problematic for physics, as the results suggest that not only are galaxies moving away from us at an ever-increasing rate, but our universe must have been expanding for a long time already. Hence, if we were to rewind the clock, surely there must have been a point in the past where all matter was clumped together in a singularity. Singularities are bad news, as that's where all known laws of physics break down and cease to be useful. Unsurprisingly, physicists are not particularly fond of singularities. Many refuted the idea of a finite universe despite Hubble's discovery. Some tried to fit the Hubble expansion with the steady-state model, like Fred Hoyle. Let's take a look at the movie Hawking, where Fred Hoyle interacts with Hawking and his supervisor, Dennis Sciama.
As galaxies move apart, new galaxies are formed to fill the gaps left behind. The new replaces the old at just the right rate. Nothing changes. Wherever you are in the universe, Andromeda, Mars, or Scarborough, it always looks the same. Because it is the same. The universe is a steady-state universe.
It is very attractive, steady-state
Cut!
theory.
Thank you, gentlemen.
And reassuring.
Yes?
Maybe it's attractive because it's reassuring. Emotionally, it's far harder to conceive of a universe that started, a universe that hasn't always been around.
Einstein?
Look what he did when his work looked like it was predicting there was a beginning to the universe. He ran away from the prospect of a beginning.
No, because he saw that a beginning would mean a breakdown of all the laws of science. How can science explain something that isn't there?
That's the thing about the idea of a Big Bang.
The thing about the idea of a Big Bang is that it's wrong, irrational and wrong. It's my term, Big Bang. I made it up. Do you know why I called it that? Because it sounds like a cartoon. Big Bang Theory is cartoon physics. Dennis agrees with me, don't you, Dennis? Lunch. The Pope is a Big Bang man.
Because?
Because before the Big Bang, there was nothing. No space, no time, no matter, no science, no rules, which leaves room for, guess who? Lord God Almighty. Religion is the enemy of science, young man. If Catholicism had its way, we'd all still be living on a flat earth at the centre of the universe with hell down below and heaven just somewhere to the left of the moon. This is 1963. God is dead. Stay away from Big Bangs. Cartoons are bad for you.
Now, unfortunately for Fred Hoyle, 1 year later in 1964, Arno Penzias and Robert Wilson discovered the cosmic microwave background, or CMB for short, which is the remnant of the Big Bang that proved the existence of a beginning for our universe that finally ended the steady-state model. Penzias and Wilson eventually won the Nobel Prize in Physics in 1978 for their discovery. We'll leave Hawking's story for another time. Today, the knowledge that the universe is expanding is common knowledge. Therefore, if we want to find the radius of the observable universe, we need to take into account this expansion as well as the age. If we do this, we find the radius of the observable universe to be 46.5 billion light years and the diameter to be 93 billion light years across. Very big indeed. But it doesn't end there. There's a little more to this. Now, if you were to look outwards into the night sky, aside from the air pollution, it would appear as if the universe was isotropic and homogeneous. These two terms are very important and forms the basis of modern cosmology. Isotropic, meaning that the universe looks the same in all directions if observed from Earth, and homogeneous, that is, the entire universe looks the same no matter which region you take, assuming you're looking on a scale large enough. In addition, although we know that the universe is expanding, it looks as if all celestial objects are moving away from us simultaneously. This leads to a very awkward conclusion that we seem to be at the center of the universe. To fix this dilemma, in modern cosmology, we use something called the Cosmological Principle. So yes, the universe is isotropic and homogeneous, but the Cosmological Principle states that this is true not just on Earth, but for all observers, no matter where they are in the universe. If one were to think about this for a while, being the informed individuals that we all are, we quickly come to the immediate consequence of the cosmological principle. If all observers observe isotropy and homogeneity no matter where they are in the universe, meaning that everything is moving away from all observers simultaneously, it would require the universe to be infinitely big. That is the only way for the cosmological principle to be satisfied. This requirement for infinity is actually quite a good explanation. Imagine if, on the contrary, the universe was very, very big, but not quite infinite. No matter the shape or size, there will always be a region somewhere defined as the center of the universe and the center of gravity. This would cause the universe to collapse, and of course, we do not observe this. But if the universe is truly infinitely big, where does it expand into, and how is it expanding? The answer is that the universe expands in space. In other words, space itself is expanding, and is what causes the distance between galaxies to increase as Hubble observed. So the universe is effectively expanding from a smaller infinity to a larger infinity, such that the overall density of the infinite universe is getting smaller. Confused? Yes, there are different sizes of infinity in existence. George Cantor was the first person to properly tackle the problem of infinity, but I think we will have to leave this for another video. Now, even though space is expanding, the distance between nearby objects are not. The Earth, for example, is still rotating around the Sun, and that is because the gravitational force of the Sun on the Earth far exceeds that of the expansion of the universe between the Sun and Earth. Put an object far away enough, however, and the gravitational force will be too weak between it and the nearest celestial body, and the universe expansion, or using the correct nomenclature, the Hubble flow, will dominate over any lingering gravitational forces. This will then in turn create the apparent paradox that everything is moving away from that observer, making it feel as if it was at the center of the entire universe. And so, to conclude, this infinity is indeed the real size of our universe. In fact, this is the only thing that the steady state model did get correct. The universe is indeed infinitely big. Thank you for watching. We are a new channel and would love to have your support. If you enjoyed this video, please subscribe and we hope to see you next time.